So first, a little bit about motion. Here's an example of what we tried to do with the strobe light earlier, taking a bunch of pictures simultaneous, or one after the other. These are probably like all a tenth of a second apart, maybe, and superimposing them together. So, how would you describe this person's motion, do you think? Any words come to mind? Awesome, I know, but that's actually me. Just kidding. How would you describe that motion? Why would you say that? Good, and we know the pictures are all the same time interval apart from each other, and these gaps are getting bigger along the way. Is that what you're going to say? Why does it get faster, do you think? Gravity, brilliant. Good, we can see that he pushed off the ground, went up a little bit, and now he's falling down from gravity. Very good. This is a picture of a cheetah about to kill a bunny. Not really relevant to anything else, but it's in the PowerPoint, so we should discuss it briefly. There you go. What's that? It's like dinner.
No, it's like on its side or something?
The cheetah was turning, I think. So have you ever like run really fast, tried to turn, you end up like leaning a little bit, like out maybe? Well, I don't blame you, but you know. Yeah, I think he or she is running after the bunny. So there you go. There's 4 kinds of motion we'll discuss this here. Straight line motion, what we're doing now. Circular motion, which we'll do later. Projectile motion, which we'll also do later. And then rotational motion, which we really won't do. So we're going to watch a movie of a glider, not a movie, pictures of a glider going across an air track. This is an air track. It's a little track, like an air hockey table. Air comes out of it to make no friction. And this glider is going to start here at 0 seconds. After 0.2 seconds, it's going to be here. So it's moving, and then it's here at 0.4 to 0.6, it's here. After 0.8, it's there. So you see how it moved along the thing there? So we can make this now into like a motion map superimposed image thing. We have 5 images from the same angle taken at even time intervals. So we're going to take those 5 images, we're going to smoosh them together, mash them up. We have this thing that comes back out, where all of these images now spaced out. And so how would you describe the motion of the glider?
Magic.
Fantastic, because it's all evenly spaced and even time intervals. That's another example of a motion. We'll always use, remember we always use that particle model, so we just use dots instead of drawing out the whole shape, but it's the same idea. You can just draw a dot like here, 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 here. The other thing you'll do, besides just drawing a dot there, let's do this now, is so I'm going to draw a dot for each of these, you know, the glider, draw a dot there, dot here, dot there. That's my, my motion map basically. We're also going to draw arrows to show the motion of the vehicle. So we'll draw an arrow like that to show that it's moving. It should be straight, sorry. That's our motion map, one of the looking arrows on there. And we'll do another example of that in a moment. So that's the basic idea we're going for. That slide broken. So how would you describe the motion of the soccer ball? Soccer ball? It's not moving, right? It's one picture. So it's not moving at all. Trick question. How would you describe the motion of the skateboarder? Constant, evenly spaced. Each picture like 0 seconds, 1, 2, 3 seconds, evenly spaced. What's this chick doing? Speeding up. What's this car doing? Which of these 3 is going to constant speed? Which is B, everyone agree? Which one's speeding up? How do you know? It's further apart. We know each of these are the same time interval apart, more distance every second. Which one's slowing down? Woo-hoo. Nice job. Questions so far? One more thing we're going to do. So, when you have a motion map, you have, as I mentioned, we have one axis that we're going to have. We just have the position axis. Let's do this one purple. We just have the position axis. It's going to look like it's just well, X for position in meters, and you would like number that if you had numbers 0, 1, 2, 3, 4. We draw a dot for each second of time. So what time is our first dot at? Usually 0 seconds. So let's say this thing's moving at 1.5 meters. No, that's too complicated. Let's do 1 meter per second, just to make it easy. So our first dot goes right here at 0 meters. That's 0 seconds. Where's the next dot going to go? At 1 meter. And that's 1 second. Where's the next dot? I know, this is tricky. Like that. Now we have to add those arrows in. The arrows should be as long as that dot would travel in 1 second. So these arrows would all be 1 meter long. Nice.
Let's have a spongy day. Bye, guys.
Like that.
Bye.
How would the question so far? How would the corresponding position graph look for this motion map? Straight line going up and to the right. Very good. So it looks like this. X, T, 4 meters, 4 seconds. Good? What if I wanted this thing to go back to the left now? How would this graph look? What? They come down like this, right? So I can do that now in 8 seconds, like that. So now the question is, how do we handle the motion man? Where should the next dot go, do you think? Why, so someone was saying over the 3, why wouldn't I put this next dot for 5 seconds right there? Good, that would show that I stopped, because I have 5 seconds and 4 seconds, both over 4 meters. And for 1 second, I didn't move, and that's not what I want to express. So it would not go there, add dot. It would go back, we travel 1 meter back, it'd be over the. It'll go back right there. Yay. Now, we would still leave this same arrow right here, but at 4 seconds, the object was moving at 1 meter per second right. At 4.01 seconds, that's when it turns around. If you don't remove that arrow, the arrow is still telling you what was going on at 4 seconds. But we know from our graph, at 5 seconds, it was back at 3 meters. Draw our arrow, dot, arrow, dot, arrow, and then our dot for 8 seconds should be back at 0 meters as the graph indicates. You can finish with an arrow if you want, and then it's done. Questions about the math? Yes? You could do the other object. So now say another one, you would, pick a different color or whatever, and you would go up here and draw it. Because there is no vertical axis, and so you can do that. Now what you want to be careful of is kind of making sure, if, let's say the second object was doing something like that, like the same thing but started 2 seconds later. So you want to be labeling at 0 meters this thing, that dot you label 2 seconds for the second object. You want to make sure you label it somehow so you know what's happening. Answer your question? Anything else? Yeah. No. What you want to do probably is label the first 1 or 2 dots. We'll eventually want to do maybe just right on the side. The delta t was 1 second, or if it was half a second, whatever it is for that problem, you should label that somewhere. Yeah. Good question. So let's just say, when you don't, let's say this thing was going to go, then it's going to stop, and then whenever it starts again, you would just then draw an arrow and start going. And this would be if this is another dot right there, that would be a 1, 2, 3 second stop. And then it's going
down, drop it,
down.
Well, I mean, it's like the left.
To go left, I would just, from here, I would just start.
Stop and then mark.
Yeah. Because up doesn't mean anything to us. Because like in theory, these three dots should be on top of each other. But since there is no y-axis here, we can do whatever. Like every one of these lines could be further up vertically than the prior one if we wanted. But that's obnoxious to do it that way. You could if that makes, it doesn't matter. If you wanted to go down instead of up, that'd be perfectly great. Left has to go up. Yeah, doesn't matter if you go up or down. I've just always gone up. Anything else? Good question. Good question. Okay. Woo! Nice. I just got worksheet 1 back out.